Did you guys have a nice weekend? Relaxing? Or did you have to shovel a lot? Who shoveled? What good helpers? That's good helpers right there. All right, so we'll do 5-3 day 2 today. We kind of introduced it on Wednesday. It was you were supposed to copy the properties to kind of help ahead of time and then do a couple homework problems. The properties are kind of what we're going to be dealing with today and then get into a little bit of fundamental theorem. But we talked about that, the abstract idea of it, and then how it becomes a reality for finding displacement last Wednesday. I know it's been a while. Do you remember that conversation at all? It was life-changing. I mean, you probably needed the full however many days off to like fully digest that. Okay, like a good sauerkraut. This is getting weird. All right. Tomorrow we'll finish up 5-3 if we need to, and we'll begin a quiz review, which is going to unfortunately take us a couple days just because of the late start on Wednesday. Looking like a quiz Thursday. There's our joke lever.
Oh, yeah.
And what else do you got here?
My posters that I'm supposed to take to mentoring, and then I left them.
Oh, the love is red. I read it as campus cash.
Yeah. I couldn't read either, so where they were.
It's okay, it's not your fault. Bye, Mary. All right, I believe this is the problem we left off with on Wednesday. Is this the last one you guys have in your notes? No, wait, hold on. We actually got to this one that was not possible. Remember that? Awesome. All right. This is very, very important that you write down. Okay. And if you want to call it, I'd probably write down the heading of average. You're most likely going to see it called the average value of a function. The average value of a function. Okay, I'll go over there, but I'm not going to the hall. Now, I'll admit, I have excessively applied this idea to the velocity function just so it sinks in as to what you're doing and the meaning of it and not be some abstract process that you just kind of do. So hopefully this will just kind of be an extension of that. Now, what if we're finding the average value of the velocity function? So with my application, what if we're finding the average value of the velocity function, v of t? Do you agree it would be 1 over b minus a times the integral from a to b of what? What would go in the integrand? V of t, right? If this is finding the average value of f and f goes in there, then if we're finding the average value of v, then doesn't v of t goes in there? V of t go in there? That would be dt instead of dx, but v of t dt. Now, help me out. We're going to do it both ways and try to find out, like in general, how this is going to work. What is this called? Ignore the 1 over b minus a for a second. What does this mean right here? Integral from a to b of f of x dx. Who can remind us what that's doing? Not how to do it. What's it doing? Cool.
The area underneath the vector in the interval dv.
Perfect. Good. Now, second question. How did we figure out that we're going to do that? Big idea on Wednesday. Huge concept. Take the antiderivative, plug in, b, plug in, and subtract. So isn't this capital F of b minus cap, this thing's really glitching out, bear with me here, minus capital F of a. No absolute values, those are parentheses, all right? Capital F of b minus capital F of a. Do you agree? Now, that is not what this slide is saying. This slide is a special application. You're only going to do this process if they say, what's the average value of whatever on this interval? This is where we actually have to multiply times 1 over b minus. All right, this is not sustainable. Mind your own tabs. I restarted this morning. Sometimes Adobe causes problems. All right, so what's the net result here? Isn't this going to be capital F of B minus capital F of A divided by B minus A? Do you understand what I'm saying here? Capital F of B minus capital F of A. If it's times 1 over B minus A, that goes in the denominator and it's over B minus A. That is a special process. It's going to be a numerical answer. And what's that numerical answer going to mean? It's the average value of F on an interval. What does that mean? Well, we'll talk about that in a minute. Let's see if it makes more sense with this application. All right, same process, different function. We know the antiderivative of v of t, don't we? When we go to take the antiderivative, plug in b, plug in a, and subtract, we know the name. It's not capital V, right? We have a name for it because it's an application. What is the antiderivative of v? Position, good, we call it s. S of b minus s of a, and because it's times 1 over b minus a, isn't it going to be this? B minus a? Ooh, we know that guy. Who is that? Huh? Yeah, in this context? What kind of velocity? Instantaneous? Average. Oh, displacement over time. Displacement over time. Meters per second from A to B. Ah, that's an average. That's an average velocity. It's the average value of the velocity function. It's an average velocity. Does that make any sense? So because, ready, general? The area under a velocity function is displacement. The area under a velocity function is displacement. Then it makes sense if you multiply times 1 over the width of the interval, you're going to get an average velocity, displacement over time. Does that make sense? All right. Average value of the function. Let's do an example and then talk about what it looks like visually. All right. 2 minus x squared on the interval from 0 to 4. Find the average value. Average value. Well, average of f. Go ahead and write this down. What's b minus a in our context? 1 over, good, 4, times the integral from 0 to 4 of 2 minus x squared dx. Now, they want us to use a calculator for this. We're going to practice. I think you guys are ready for this. We've taken enough time on this. We're going to practice our process we're going to be using for the rest of the year. All right? If this were called little f of x, our little side work is, well, I'm going to find capital F of x. I'm going to plug in 4. I'm going to plug in 0. I'm going to subtract. Then I'm going to multiply by 1/4. Right? What's capital F of x? Well, what's the antiderivative of 2 with respect to x? Antiderivative. 2x. Minus, what's the antiderivative of x squared with respect to x? Good. 1/3 x cubed plus a constant that could have been there and disappeared when we took the derivative. Now, for those of you who like maybe need things repeated frequently, the way we take an antiderivative, we add 1 to the exponent and we divide by the new exponent. So we added 1 to the exponent, got 3. And then when you divide by 3, it's the same as multiplying by 1/3. So add 1 to the exponent, divide by the new exponent. Now, what are we supposed to do? For this part of the process, isn't it going to be capital F of 4 minus capital F of 0? So we should probably do some side work and say, what's capital F of 4? And what's capital F of 0? What's capital F of 4? Well, 8 minus, what's 4 cubed? 64. So 8 minus 64 thirds plus a constant. And then what's capital F of 0? Just C, right? So we're going to have 8 minus 64 thirds plus C minus C. And this is all getting multiplied by 1/4 at the end. So as we do these, I kind of want you guys to, I definitely want you guys to understand what you're doing. Do you agree that the part in green is finding the area under the function from 0 to 4? The part in green finds area. The 1/4 averages it. Okay? So we'll save that 1/4 for the end. Isn't 8 24 thirds? What's 24 thirds minus 64 thirds? Negative 40 thirds. Plus C minus C. Times 1/4. What do we get? What is it? 40 over 4 is 10. Negative 10 thirds. It's a good thing we had so many days off. This board would have been punched by now. Oh, man. Never did I ever wish we did that. All right, negative 10 thirds. Negative 3 1/3. What's that? That's the average value of F. But the area The area was negative 40 thirds, wasn't it? The area was negative 40 thirds. The average value was negative 10 thirds. Let's graph this and see what's going on. So we got 2 minus x squared from 0 to 4. 2 minus x squared. Graph. Then you window 0 to 4. Now, what was the height at 0 on the original function? 2 minus x squared. 2 minus x squared, a height of 2. My y is good there. What is the height at 4? 2 minus 4 squared. 2 minus 16. What do we get? Negative 14. So I probably want to change my y min to like negative 14. Okay. So we're seeing everything here. I want you to take a minute and remind yourself, when we find area under a curve, which part is it finding and calculating? Well, here's what it's doing. It's doing area, 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 area. And do you guys see it's doing this area, right? When the function is negative, it's actually above the function to the x-axis. And what's it doing? It's taking this value and adding them. A positive area, a negative area, and combining them. I walk to the right, however many feet, meters, whatever. Then I walk to the left. It looks like I've walked to the left more than I walked to the right. Do you agree? So I would expect a negative net area. Let's figure that out. Ready? Menu, analyze graph. Let's do the integral from 0 to 4. The net area is negative 13 1/3. Where'd that come from? What does that correspond with in our problem?
Negative 40 over 3.
Negative 40 thirds. So what was the negative 3 1/3? Negative 10 thirds. That's a constant. Negative 10 thirds was the average value. What does that mean in our context? Anybody know? Negative 10 thirds. Cool.
I know the interval times that, or the integral for that equation is the integral for the F1 third equivalent integral, but I don't know.
Do you understand what that red line means? It's the average value of f. Do you know what that means, though? Because f is not constant, right? F is not constant. You can't just say, oh, here's the highest point, here's the lowest point. It's in the middle. Do you agree f is it's decreasing relatively slowly and then fast? Yes? This process actually finds the average y value on the graph. If you were to add them all up infinitely many times and divide by infinitely many inputs. It's the average height that you're looking at. It's the average f of x. It's the average y value of that graph you're looking at. Does that make sense? So context, ready? I start here, I walk to the right, I walk to the left, I calculate my displacement. What was my displacement for this problem? Negative 40 thirds, very good. Negative 40 thirds, which is negative 13 1/3, is how far I have been displaced from where I started. So I'm actually negative 13 1/3 feet to the left of where I started. That's the area. That's the area context. So what's the negative 3 1/3? Oh, on this number line, ready? Let's say I started at 0. On this number line, I walk to the right, okay, up until here. Then I walk to the left. My average position was negative 3 1/3 as I was walking. My average position was negative 3 1/3. Does that make any sense? Okay. Another application. All right. Let's make this realistic. You go to Cedar Point, you're waiting in a line. Okay. And someone who has no life decides to calculate the average number of people waiting in the line at a given time. Okay? And they somehow found out a function that had so many people per hour were being added to the line. People per hour were being added to the line. Okay? They found the antiderivative of that people per hour function, and they divided by, they found the antiderivative, they plugged in the starting time, or any time and starting time subtracted. Okay? And then multiplied by 1 over however long was being calculated. They found the average, what? Number of people standing in the line. Okay? They found an average number of people standing in the line. Does that help at all? I don't know. There's a lot of applications and context to this. All right? Don't want to overdo it. So, you're going to be asked this 2 different ways. 1, find the area. Green. This green, negative 40/3. But if they want you to find the average value of the function, they're going to have to tell you that, because you're not going to do that automatically. You would do this green process 9 times out of 10. If they want average value, they're going to have to say average value. Okay? It's a special application. All right. Now, here is an extension of that average value problem. What if I said, at what time did the function hit its average value? Wouldn't you set the blue curve equal to negative 13 1/3 and find out where that happened? Right? And I bet this is not difficult for you guys to put together. If the average value of a function is here, it has to hit its average value on the interval at some point in time. If it had an average value of this, the function, it could have hit it early on, it could have hit it later on, or right in the middle, somewhere in between. It had to hit its average value somewhere. That is what this theorem is saying. There must be a point C, an x value, where the function at that C value equaled its average value. F of C, that's where it hit it. Okay. That's the mean value theorem for definite integrals, which probably sounds familiar. Remember the mean value theorem? Driving on a highway, toll booth, right? Oh, your average speed was 80. You must have been going 80. Right? Mean value theorem. Instantaneous velocity must have equaled the average velocity. It extends to definite integrals as well. Your average value, average position, must have been hit somewhere on the interval. All right. And this is the extension. This is just another visual for it. All right. If you were to take your average value times your base, that rectangle is the same as the area under the whole curve. All right. Last, I better not promise that. Yeah. Last idea for today, but it's kind of a heavy one. So bear with. I think you guys are well prepared for it because of that worksheet. You've already kind of done this. So write this down. And it says the derivative of an integral. We're also going to call it the fundamental theorem of calculus, part 1. What's the fun in fundamental theorem? Thanks, Lane. Madison, did you get your car plowed out? Yes. Did you hand shovel it for 4 days straight?
No, I didn't.
Did you pay him?
No. He just did it.
What a brother. He does have a lot of energy. You gotta get it out somehow. My son came out to shovel for like 5 minutes and then said it was too cold. And went in. So I threw him in a snowdrift. Is this earth shattering to you or not? Do you understand what it's saying? You guys are quiet today. It's a Monday. How many of you understand what it's saying without any explanation? Be honest. All right. Worksheet, column 1, column 2, column 3. All right, from henceforth, I will call this column 1, column 2, column 3. Remind me, what was the big idea here? Who could raise their hand and explain this other than Cole? Okay. Cole to see? Dom? Tyler? Caden, yes.
The area function was equal to the antiderivative of the f of t function.
Very, very nice, very nice. And then, doesn't have to be Caden. Column 3, we took the derivative of that area function, and we got back to column 1. Right? Everybody good with that? Let's break this down. Okay? All of this is saying is, I need you all to, I really need really good focus here. Okay? They test this, obviously a ton. It's called the fundamental theorem of calculus. It's gonna be a big idea. All right. This right here is column 1. Do we all agree this right here would be column 2? Can you help me out with that part? How would I find, I don't know what f of t is. Symbolically though, I can write out an equivalent expression for column 2. So column 1 was f of t. Let's fill in column 2 here. Make me proud. Big F of x minus big F of a. Does everybody agree with that, or does it need adjustments? Well, fine tuning, or is it good? Capital F of x minus capital F of a. I don't know what it is, but that's how I would write it. If this were if little f of t were quadratic, and I want to leave this abstract for a reason, but I want it to be concrete at the same time. So what if little f of t were t squared? What would column 2 be? Well, what's the antiderivative of t squared? So big F of t would be 1/3 t cubed plus a constant, right? And how would we find this? Well, we would take that antiderivative, plug in x, plug in a, and subtract.
So we'd get capital F of x is 1/3 x cubed plus c. Capital F of a, where a is a constant, would be 1/3 a cubed plus c. Wouldn't it be 1/3 x cubed minus 1/3 a cubed? 1/3 x cubed minus 1/3 a cubed. Are you with me? Let's subtract it. 1/3 x cubed minus 1/3 a cubed, where a is a variable or constant? Constant. A is a number. A is a number. Ready? F of x, function. F of a, number. Constant. Good? That's important. We'll come back later. Again, I don't want this to be what you dwell on, but I want you to at least be able to connect it. But wait a minute. There's more. Well, it sounds like an infomercial. If you take the derivative now, I will throw in 2 free jokes for them. I don't know. We're taking the derivative of this thing. That's what they told us to do. Why are we doing that? We're not going to do that often. Because if we're finding area, you're not taking the derivative of the antiderivative function. You're just going to take the antiderivative, plug in the top number, bottom number, subtract. Area, done. This is a theorem that we're trying to put together. Ready? We're taking the derivative of this thing. Well, how many terms do you see? 2. F of x is a function. F of a is a constant. What's the derivative of capital F of x? Say it again. Little f of x. Actually, I want to, for those of you really, really tedious people, the derivative of capital F of x minus the derivative of capital F of a. The derivative of capital F of x was little f of x. The derivative of capital F of a is 0. F of x minus 0 is f of x. And f of x is our column 3, which was the derivative of this blue thing. Did that make any sense at all? It's like when you were back in Algebra 1. I don't know if the teacher explained it this way or not. But if they said, okay, what's 4 squared? And you would say 16. And then they'd say, okay, what's the square root of 16? 4. Right? If I take the antiderivative of something, and then I take the derivative of it and get back to where I started, isn't that the definition of an inverse operation? Isn't that the definition of an inverse operation? What's 2 times 100? What's 200 divided by 2? Inverse operation. Multiplication, division, inverse operations. Okay? Doesn't that make sense? Like in elementary school. One of my kids is sick. All right. Look it up here. This is the fun of the calculus here. Can't deprive you guys. Where was I?
Is that your joke on the board?
Oh, Adam. Adam, where you been, buddy? The girl that walked in. Were you here for that? We missed you. So what is this telling us? The fundamental theorem says this process of finding area
listen carefully, involves the antiderivative function. That was the big idea. How do you find area? Antiderivatives. So what happens if you take a derivative of that? Oh, derivative of an antiderivative, back to where you started. That's the fundamental theorem of calculus, part 1. All right? Does that make sense? All right, now I want to challenge you. First of all, solve this the way you think you should solve it. I think you're going to get it right. I'll just tell you this. There's no derivatives involved here, just area. Okay? But then we're going to turn it into something more interesting. I'll tell you what, we're actually going to do a 2-for-1. Since I probably have to make a phone call, I will put this here, buy myself some time, and you will have 2 problems to practice. I know, hold on.